And this is actually a particularly useful feature in other cases as well. Let's say if you want to develop a piezo transformer, and to measure the gain, you would need some kind of a resistive load. And to add a resistor to your model, you can use one of these components which is shown on the left side. You can add resistors, you can add that as a load, and you can calculate the gain of a piezoelectric transformer, for instance. And then, as I had mentioned earlier, the MEMS module is actually very unique because it also includes not structural and the electrical part, but it also includes a fluidic simulation. So you can do microfluidic simulations with the COMSOL's MEMS module. Microfluidics by itself, it's a very vast area, and it might be difficult to cover it entirely in this webinar, but let me at least highlight some of the key features then. There are some special interfaces and boundary conditions to deal with fluid flow, especially in the microscale. You can solve for laminar flow, which is basically incompressible Navier-Stokes, and you can also solve just Stokes flow equations if you wanted to. Stokes flow, for those who do not know, is very similar to the Navier-Stokes equations, but it's except that the initial or the inertial term goes to 0 here. And these are suitable mainly for flows with very low Reynolds numbers. You can model single-phase flow, you can model multi-phase flow, which is basically two-phase flows, which is capillary flows. You can actually model inkjets, you can model bubbles in your flow and things like that. And there are also situations where electrical energy is the driving force for, say, fluid flow in microscale. We will talk about that a little more in the next slide. It is important to remember that COMSOL is actually a very versatile tool, and say for an example, you can model flow in the microscale, you can couple it with structural deformations, and then the flow doesn't have to be a single phase flow, it can be a multi-phase flow. So it has a multi-phase flow going through a microscale channel, and you couple structural deformations with it. So you can actually make it as complicated as the application actually needs it. It's very versatile and easy to use then. So now let's talk a little bit about flow driven by electrical fields. The MEMS module can handle it, and it can simulate, say, electroosmosis for electroosmotic mixers, micropumps, and things like that, which are generally used in lab-on-chip devices. The COMSOL's MEMS module also provides an interface for electrokinetic flow, which addresses transport of ionic species, which are usually present in very low concentration, say in a moderately concentrated electrolyte or something like that. And this application mode basically models convection, diffusion, and also migration then. So the MEMS module is actually good for doing any microfluidic simulations in addition to structural simulations and electromechanical simulations. So electrical, structural, and fluidics can be taken care of. And as I had mentioned earlier, you can also include thermal analysis to any of these models. Now that we have seen some of these examples, it is also good to know that most of the coupled physics that are needed for MEMS applications are already available as a predefined template in COMSOL. Say, for example, if you are interested in modeling electrical and structural interactions all in one model, and all of them are coupled with each other, then you can go to the user interface and choose something called as Joule heating with thermal expansion. And all the necessary equations, as you can see, when I select that, on the right side you can see that the necessary equations are all come into place. The coupling between them is already taken care of. So it's basically a blank template which you can use to actually model all these interactions at the same time. You can of course include your own arbitrary coupled physics manually, that's fine. And you can even take any of these predefined coupled interfaces and you can add other physics to it. So there is absolutely no limit to the number of physics that you can actually add on to any model then. And it's all done using the same interface, nothing special, so it's very simple to do. If you really look at it, in every way, COMSOL is a truly multi-physics program. Anything can couple to anything else. It is very flexible, wherein you can add any expressions or functions in any place where you can just type in a number. Say, for example, a boundary condition or a material property. You can, if you look up some kind of an expression or a function from, say, literature, you can directly type it into that field, and you can use them in your simulations. And of course, all of this can be done quite comfortably in the user interface itself. That's basically it in terms of the examples that I wanted to show you in terms of the COMSOL examples, which are available, most of them in the model library. So when you buy COMSOL or if you're using COMSOL, most of these examples that I showed you are available in the model library. And before we move on to the Q&A session, I just briefly wanted to show you some examples from our user base. You can, of course, find many more examples from our users on the COMSOL website. The first one that I wanted to show here is a MEMS biosensor. This was modeled by Dr. Carl Meinhardt's group in UC Santa Barbara. If you look at this slide on the top right of your screen, you can see a schematic of the system that needs to be modeled. An analyte is basically introduced from the left of the microflow channel, and there are some reaction surfaces on the side walls of this microchannel. The goal is basically to get the maximum concentration of the analyte to the reaction surface. This might not be possible without the addition of an electrical field then. So the stirring of the solution in the flow path is driven by an electrical system. So it's a combination of fluid flow and electrical simulation at the time. The plot that you see on the left side of the screen is the average concentration of bonded molecules on the reaction surface with and without the electrical field. This is a time-dependent simulation. So as you can see, with the applied electrical field, there is a higher rate of reaction binding on the surface as against to lower rate when there is no electrical field then. This is one of those examples where a MEMS biosensor was basically designed based on simulations from COMSOL. And I wanted to show you one more example from one of our users. This is from ST Microelectronics, semiconductor application. In the semiconductor industry, what happens is probes are used to usually connect to electrode pads or vias, call it, in the circuit for electrical testing purposes before they actually package the device into an IC chip. Usually there are multiple layers of metals below these electrode pads or vias, which are separated by dielectric layers. These are called interlayer dielectrics. When probes are used to actually do these electrical testings, there are contact forces, and these contact forces basically destroy layers sometimes, and it basically shorts the device. So there is a device failure then. So the team in ST Microelectronics used COMSOL, and they designed probes for these electrical testing purposes then. So basically to minimize the effect of surface damage and thereby reducing the device failure rate then. By modeling the contact forces, they were actually be able to come up with a new design for the probe. So the probe tip was made longer and the structure was made thinner then. This essentially reduced the contact force by almost 30%, which essentially led to a lower device failure rate then. There are many such applications, where COMSOL can be used for doing design analysis before you actually fabricate or make the device in the manufacturing process then. And if you want to learn more about a lot of these user-based applications, then you can attend one of the COMSOL conferences. Every year we conduct a COMSOL conference in Boston and also in other places around the world. This year the Boston conference is being held between October 7th and 9th. So if you're interested, you can visit the conference website, which is comsol.com/conference2010. Here, of course, you can listen to much more user presentations. Usually, there are approximately 130 to, say, 140 user presentations just in the Boston conference alone. And this is a great source of information. You can also meet with the developers, get a chance to interact with other people in your industry. So if you're interested, go to the COMSOL conference website to get more information. And that's about it. Thank you all for attending the MEMS webinar. Please note that you can go onto our website to find more information on MEMS. You can also visit the papers section, which is comsol.com/papers, where you will find many more examples from our users. You are more than welcome to join the COMSOL community, which is hosted on our website, which is comsol.com/community. Here basically users interact with each other, they exchange models, they share news, they even exchange their models. There is a model exchange forum, so if you want, you can actually trade models among yourselves. You can visit any of these sites at any point of time. And thank you once again for attending the MEMS webinar.